Good afternoon, and well, thank you very much, Barbara and Philippe, for the invitation to this very interesting conference. And well, you may have noticed the title has changed a little bit. When Barbara invited me half a year ago, I gave her something that Dan Frost would call a placeholder title. And when I started to think about what to really tell you last weekend, I found I should be a bit more specific. And so what I will talk about is, well, iron snow dynamos in Ganymede and in Mercury. So the thermal conductivity of iron alloys in the cores of the planet is rather high. And along an adiabatic temperature gradient, which you expect in a convecting fluid, you can actually transport a rather substantial heat flow. The heat flow out of the core of a planet, of a rocky planet, is set by the mantle. And at least today we can assume that for at least all the smaller planets, this heat flow out of the core is less than the conductive heat flux along an adiabatic gradient. And this may even hold for the Earth today. As we have heard in the last talk before lunch, there has been an upward revision of thermal conductivity in the Earth's core. And so even for the Earth's core, it seems possible that the heat flow is less than adiabatic. And to get convection in the core as a prerequisite for a dynamo, you can do it only in the circumstances if you have a phase change of iron, basically freezing out iron. And then the main driving agent is the associated separation of the light element that becomes enriched in the residual liquid. And of course, we all know for the Earth, the inner core grows with time, expels the light element, probably oxygen, as we have heard before lunch, which drives compositional convection. And the question, of course, is, can this be the prototype also for other planets, particular smaller ones in the solar system? Now, for the smaller planets, sulfur is the preferred light element because oxygen doesn't dissolve at low pressures very well, whereas sulfur basically dissolves in iron also at very low pressure. And the effect of sulfur is to reduce not only the melting temperature, but also the gradient of melting temperature with pressure. So this here is a phase diagram for iron-sulfur alloys, pressure on the x-axis, temperature on the y-axis. I borrowed this from a paper by Rivaldini a few years ago. And what you see here, this is a melting curve for pure iron. And these gray lines show the melting curve for an increasing amount of sulfur in the alloy. The blue lines are adiabatic temperature gradients. And if we have little sulfur, we have a situation as we have it in the Earth's core. So the melting gradient is steeper than the adiabatic gradient. So if the temperature drops in the core will start to crystallize from the center. However, this situation may change at higher sulfur concentrations, and in particular in the pressure range up to 10 or 11 gigapascal here, which is the pressure range in the core of Ganymede. As you see, the melting temperature gradient decreases and even becomes negative for high sulfur concentrations. And in such a situation, the crystallization of the core will start top down. And if we have such a scenario, what does it mean for driving convection? So the iron that crystallizes, of course, is still denser than the fluid. So kind of iron snow will form near the core mantle boundary and will sink under gravity. The residual liquid, if you take out iron, becomes enriched in sulfur. so it becomes more buoyant and will stay below the core mantle boundary. And eventually, a scenario, as is shown here in this diagram, may develop. So this has been adapted to the situation as it may be in Ganymede's core. So after a while, we have a snow-forming layer, which is this bluish region here. And the blue curves here are the liquidus temperatures for various sulfur concentrations. The black line are adiabats, and the red line is the actual temperature at this instant in time. So in this snow-forming layer, a state will develop where the sulfur concentration and the temperature are arranged in such a way that we are at every point at the liquidus. And as the cooling proceeds, snow will crystallize throughout this layer and will think. As these snowflakes fall out of this layer, getting into the central region, here the temperature is above the local melting temperature. And so if these snowflakes don't become too big, then they should dissolve again. So at the top of this interior region here, we have a flux of iron that enriches the central fluid in iron or depletes it in sulfur. And in this way, we can drive compositional convection by this iron influx from above in the central part of the core. In contrast, this snow-forming layer, because of this compositional gradient here, is very strongly stably stratified, compositionally and also thermally, because the temperature gradient is less than the adiabatic gradient. So this scenario has been discussed by Stephen Hawke, together with some other possible scenarios, coupled almost 8 years ago. And so this shows a cartoon picture of basically the same story. The shades of blue indicate the sulfur or the iron concentration. We have the snow-forming layer. And because it's very strongly stable, the stable density contrast across the snow layer is roughly 5 orders of magnitude larger than a typical density contrast that drives convection in a homogeneous fluid. So it's very strongly stable. So we expect that we can't have any overturn in this stable layer. However, horizontal motion is still possible. The system will evolve with time as it cools, and the snow layer will grow downwards more and more, and eventually it will reach the center. And at this point, the iron snow can no longer melt, but rather it will accumulate into a growing inner core. But in this stage, the whole remaining fluid is stably stratified, and we can't have convection, we can't have a dynamo. So for Ganymede, let's assume that we haven't yet reached this stage, but rather we're in a stage as is depicted here. Okay, so a dynamo, such kind of dynamo model, would it be able to explain any properties of Ganymede's magnetic field better than any other dynamo model? And so let's look what we know about Ganymede's magnetic field. The Galileo mission detected, rather surprisingly, that Ganymede has a global intrinsic magnetic field. It is mainly dipolar, with an equatorial field strength of a little bit more than 700 nanotesla, so not a very strong field compared to Earth. The dipole tilt with respect to the rotation axis is small. And Kivelson and co-workers, when they analyzed the magnetometer data from the 4 or 5 useful flybys, they found they could explain the data with 2 different models. In the first model, they assumed a dipole plus a quadrupole, which turned out to make a weak contribution. In the second model, they had the internal dipole plus an induced field in a salty ocean inside Ganymede, induced by the time-changing field of Jupiter at the point of Ganymede because of the planet's rotation and the tilt of Jupiter's spin axis. And in the second model, they don't needed any additional quadrupole. Well, we believe today that an ocean in Ganymede is quite likely. And therefore, it might be reasonable to assume that the quadrupole contribution of this first model can be considered an actual limit, an upper limit to the actual quadrupole moment of Ganymede. Of course, really completely we will know only after the JUICE mission has been in orbit around Ganymede, so we have to wait until 2033. But up to that point, let's assume that the quadrupole from model 1 is an upper limit for the actual quadrupole. Well, Ganymede is basically a three-layered structure with the ice or water layer on the outside, a rocky mantle, and a metallic core. Metallic core very likely because it has been speculated but then rejected that a dynamo could operate in a salty water ocean. So there's probably a metallic core. The radius, the size of the core is rather uncertain, but a plausible, perhaps a likely range is between 1/4 and 1/3 of Ganymede's radius. Now the quadrupole is weak, as I mentioned. Of course, as you downward continue the field as a potential field, the quadrupole to dipole ratio will increase because the quadrupole drops off like the 1/radius to the 4th, and the dipole as 1/r³. But still, even if we assume a rather small core with 1/4 of Ganymede's radius, then the quadrupole to dipole ratio at the top of the core is unusually small. So the ratio in power of the quadrupole to the dipole is less than 4%. To put this into perspective, at the Earth's core mantle boundary, this ratio is 14%. And also for the other planets, it's in this range or sometimes much larger. So Ganymede has a weak field, and it seems to have an unusually low quadrupole to dipole ratio. Of course, this could be by chance, just in the present epoch, may change, but let's see if there's a better reason. So I did calculate a number of numerical dynamo models for this iron snow layer scenario. So it's a usual MHD dynamo model in a rotating sphere, and here the dynamo is driven by a buoyancy flux from above, which represents the melting iron snow. I retain a small inner core only for technical reasons, and so this is completely passive. There's no buoyancy flux coming off the inner core. The snow layer here is treated as a completely separate layer. It is electrically conducting, but it's very strongly stably stratified, with the consequence that I allow only for horizontal motion in this layer. And this motion is driven by, well, Lorentz forces, inertia, and so on, and it's coupled viscously and magnetically to the underlying dynamo. In addition to these snow layer models, for each case I've also run a reference model where there's no extra outer layer, just to see what makes the difference. Okay, I varied some of the parameters. If these parameters and these numbers don't mean much to you, don't worry at the moment. Perhaps the only point to mention here is I varied also the thickness of the stable layer between 7% and 39% of the core radius, or in absolute terms, something like 50 to 300 kilometers. Okay, here are snapshots of the radial magnetic field for the reference model and the model with a stable fluid layer, which has in this case 24% of the core radius. Actually, the field of the reference model is not shown at the top of the dynamo, but has been upward continued over a distance that is equal to the thickness of the stable layer in this case, just to have a better comparison. So both are obviously dipole-dominated magnetic fields. However, in the reference model without the stable layer, there's a significant quadrupole which becomes obvious from this dichotomy of magnetic flux in the eastern and the western hemisphere. So this is a G21 or H21 term, which is quite significant in this case. With a stable layer on top of the dynamo, the field is quite a bit more axisymmetric and more strongly dipolar. If I look now at magnetic power spectra as a function of harmonic degree, this is the result. So the filled circles up here is a spectrum for the reference case. Everything here is averaged in time and normalized to the dipole being equal to 1. And for comparison, these little crosses show the spectrum of the Earth's field at the core mantle boundary, and it's quite similar to that of the reference model. The triangles is a spectrum for the model with a stable layer, and there's a strong reduction by more than an order of magnitude in the power of the quadrupole and also of the power in the higher multipoles here. Some part of that is simply due to the geometrical effect of propagating the field through the stable layer, because higher multipoles drop off faster, even if it's simply a potential field. And to show this, this is shown by these gray circles here. So the gray circles are for the case without the stable layer, however upward propagated over the thickness of a stable layer. And as we see for the quadrupole, it has really only a very small effect. And in addition to that, there's another order of magnitude drop. For the higher multipoles, it can be more significant. The green line here shows the upper limit for Ganymede. And for the reference model, we are a little bit above with the quadrupole power. With the stable layer model, we are far below. What's the reason for this strong reduction in power of the quadrupole? Well, it's an electromagnetic skin effect, basically. This shows a time series for one of the quadrupole components, the G21 Gauss coefficient. And the black line is for the field at the interface between the dynamo and the overlying stable layer. So we get these strong fluctuations here. The red line is, in the same model, the time variation at the top of the stable layer. We see a strong reduction in amplitude, and the short period fluctuations, which are present here at the top of the dynamo, they are completely filtered out. The longer period variations, with time scales here of 500 to 1,000 years, they can pass to a certain degree. However, they are attenuated by a factor of 3 to 4 in amplitude and 10 or 12 in power. And this is exactly more or less what you get if you stick it in simply in the equation for the skin effect, with the thickness and conductivity of the stable layer, gives a very similar result. So it's a skin effect which attenuates the rapidly fluctuating quadrupole components. Why does it not affect the dipole in the same way? Well, the dipole, the axial dipole, is special. It also has a short period fluctuations, but these right on top of a DC, a constant component, constant polarity component that persists for a long time. And this DC component obviously is unaffected by a skin effect and can reach to the outside. And in addition, it sees that also in the stable layer, we get some horizontal flow, some zonal flow, which additionally damps the non-axisymmetric field by just shearing it apart and transforming it from to higher harmonics and damping it out. Well, this was for one model. So here's a rather larger set of models where I varied the parameters, like the Ekman number, the Rayleigh number. So what's plotted here is the ratio of quadrupole power over dipole power ordered here as a function of the magnetic Reynolds number. And the color scheme is the white symbols are for the reference case without stable layer, and then the darker or colder the color gets, the thicker is the stable layer. And, well, just as expected, well, even for a rather thin stable layer, which covers only 7% of the radius of the core, there's a significant effect by a factor of 4, damping, compared to the reference model. And as you increase the stable layer thickness here, the damping becomes even stronger. And this broken line here is the assumed upper limit for Ganymede. So the reference models without stable layer are usually above this upper limit. Some are marginally compatible, whereas all the models with a stable layer are well below this upper limit. Okay, what about the magnetic field strength? We have seen Ganymede has a rather weak magnetic field. The main reason why the field is so weak is because the core is rather small. And of course, we observe the field at or above the surface of Ganymede. But now, what about absolute numbers? Well, as you may know, that dynamo models have a notorious problem that we can't run them at the real parameters of a planetary core, like the real viscosity. We must assume much too large viscosities. Here, if I rescale this model from non-dimensional to dimensional numbers, I also find that the rotation rate is too slow by a factor of 20 or 10 to 20 here. However, scaling studies suggested that the magnetic field strength is mainly controlled by the buoyancy flux or the power that you can put in to drive the dynamo. So the most important part is to get a reasonable value for the buoyancy flux. And what I took here is 10,000 kilogram per second, which came out of thermal evolution simulations of a snow layer scenario by the DLR Berlin group here. Okay, and if I do this and then rescale everything to get the axial dipole Gauss coefficient here for these three models with different thicknesses of the stable layer, well, they are more or less all in the right ballpark. Remember, for Ganymede, it's 710 nanotesla, the G10 coefficient. So they are all in the right ballpark, and in particular for this model here in the middle with a 14% stable layer, we are more or less precisely where we want to be. So this kind of model suggests an explanation for the weak quadrupole. It's no proof, of course, that it works this way, but at least this observation can be explained. Okay, so far I didn't show all the models because not in all cases I get a dynamo with a dipole-dominated magnetic field. This here shows a kind of regime diagram. What's plotted here on the y-axis is the relative thickness of the stable layer, and the ordering parameter on the x-axis here is the Rayleigh number times the Ekman number to power 9/4. Well, don't worry about why exactly this parameter here. But there are two regimes where we have these greenish symbols, we find dipolar dynamos, and where we have the red symbols, we find non-dipolar, in particular mostly so-called hemispherical dynamos. And well, as we increase the stable layer thickness, we find that at first a thin stable layer favors a little bit the dipolar mode. But as we get to very thick stable layers, more than, say, 30% of the radius, then this hemispherical mode becomes strongly favored. So what does hemispherical mode mean? This kind of dynamos have been found in numerical models by the group of Fritz Busser quite some time ago, and have been studied in much more detail by Landau and Ouvert a few years ago. Basically what we get is This here shows on a cut along the rotation axis the horizontally averaged temperature, or if you want, light element concentration. So there's a strong dichotomy with one hot and one cold hemisphere. And the dynamo actually works only in one of the two hemispheres, the cold one here. And it results in a magnetic field that at some little distance above the top of the core may look like that. So we have the strong magnetic flux emerging near one pole, and then the opposite flux in an equatorial belt, and then at the other pole, very little is going on. And if you decompose this into typical spherical harmonics, it means that we have an axial quadrupole, which is a little bit larger, but roughly of the same order as the axial dipole. So it's a superposition, if you want, of an axial quadrupole and an axial dipole field that we have here. Well, obviously for Ganymede, this is not a very good model, because we just wanted to explain why there is so little quadrupole. And we get very little quadrupole as long as we are in the dipolar regime, which is found, for example, if the snow layer is not too thick, which could be an argument about the present state of Ganymede. There may be a snow layer, but probably not a very thick one. However, this hemispherical mode might give an explanation for properties of Mercury's magnetic field. So Mercury, we know that Mercury has an intrinsic magnetic field since it was first visited by Mariner 10 in the 1970s. And, well, it was also a surprise to find a magnetic field at all. And the other strange feature is that the magnetic field is rather weak. It's even weaker than Ganymede's field, which is really surprising because Ganymede's metal core is small, whereas Mercury's metal core is very big. And we learned more about Mercury's field with the MESSENGER mission in orbit. And one problem with determining the details of Mercury's internal magnetic field is because it's so weak and Mercury is so close to the Sun, the external field by the magnetospheric currents are rather large and as you measure the magnetic field in the magnetosphere of Mercury, there's a strong contribution from the external field, which is a little bit of a problem in separating the two. Well, what Anderson and co-workers did in analyzing the magnetometer data was they concentrated on the position of the magnetic equator in the sense here of a zero component pointing radially away from the rotation axis. No, not from the center, from the rotation axis. And so they argue that the location of this magnetic equator is rather insensitive to well, how the external and the field looks like and combines with the internal field. And what they found, somewhat surprisingly, is a very constant offset. So this shows as a function of planetary longitude the offset in the north-south direction of this magnetic equator. So it's offset by roughly 20% of the planetary radius towards the north, with little variation in longitude. And this little systematic variation in longitude suggests the dipole tilt is small, and they come up with this number less than 0.8 degrees, which is really small. So the best way of describing the field is just by a dipole that is offset from the center of the planet towards the north. Or if you interpret this in terms of spherical harmonics that are, of course, planetocentric, it means that there's a significant axial quadrupole component. And the ratio of G20 to G10 they come up with is 0.39, which is really a rather large number. So the question is, could this hemispherical type of dynamo perhaps explain this? What we need for that would be a thick snow layer. And here the case for Mercury is much less clear. Depending on well, the sulfur content, we can have, well, here the yellow region now is the range of core pressures in mercury, and we see here the melting temperature variation has quite some complexity. And depending how much sulfur there is, we can get, well, a snow layer near the surface, but we can get only 2 snow layers with an internal snow layer. Only if the sulfur content is really large, then we are in a situation where the adiabat is everywhere steeper than the melting point gradient, and in that case we could get a steep snow layer that reaches to great depths. So not sure how likely or how possible this is, but anyway, here's a kind of model with a really thick stable layer here on the outside. So the dynamo region in this case has just 40% of the radius, and there's a very thick, stably stratified layer above, which, as we have seen, strongly favors this hemispherical type of dynamos. This shows a snapshot of the radial magnetic field at the top of the dynamo region, at this interface here. There's a lot of complexity, but basically there is flux, red flux in the north polar cap, and blue flux in an equatorial belt, and relatively little in the southern hemisphere. And if we now look at the field, well, not at the surface of the core, but even upward continue to the surface of Mercury, well, this is the result here. The color scale here is strongly enhanced by a factor 160 compared to what it is up here. So it's really a very weak field. And basically we get this strong flux near the North Pole, and then the return flux is rather weak and broadly distributed over the southern hemisphere. And the magnetic equator, a little bit hard to see here, the change from bluish to yellow is about 12 degrees north. The G21, the G20 to G10 is more or less exactly what has been determined for Mercury. Of course, I just picked this case for this reason. The magnetic dipole moment in this case is a little bit on the large side. It's about twice what's actually been determined for Mercury, but really it's roughly on an order of magnitude scale still okay, and the dipole tilt that we observe on the outside is very small. Okay, well, time is almost up. This is just showing I have more than one model, and this shows the G21 to G21 over G20 over G10 ratio. It seems to depend a little bit on the supercriticality of the Rayleigh number here, however, you find for both the 2 Ekman numbers, different symbols are different Ekman numbers, you find cases that can fit the observed ratio of Mercury. Okay, so sum up is that the cores of the smaller rocky planets, if they are composed of an iron-sulfur alloy, may well start solidifying from top down rather than from the center, and that in this case, iron snow may form in this top layer and remelt at greater depths and drive compositional convection than in the interior of the core. And a thin snow layer in Ganymede allows for dipolar dynamos and would damp the quadrupole components above the CMB to conform with observation. Bit more tentative because it's not clear if you can have so much sulfur in Mercury's core, but a thick snow layer in Mercury's core would favor a hemispherical dynamo that may explain the high axial quadrupole moment found at Mercury. Thank you very much.